Okay, first notice that this can actually be factored even more. We have a difference of squares, as it's called, x plus 1, x minus 1, all that's being squared. Which means that I can write it like this. It's x plus 1 quantity squared, x minus 1 quantity squared. Now, let's do some algebra here and come back to the calculus there. We have to decompose this fraction. So the setup is as follows. So notice that if you have a factor that is repeated, you have to build up to that power. And the same thing here. This factor had a power of 2, so I went x minus 1, and then I went x minus 1 squared. That's just how this is to be set up. Okay, so now notice that I have fractions all over the place. So I'd like to do something that will eliminate all of the denominators. And that can be accomplished by multiplying everything by the least common denominator, which is essentially all of this here. So let me show my work like this. I'm essentially going to multiply both sides of this equation by this. Now notice that here on the left, these essentially knock out, and all that you have is 1. On the right, however, you have to employ the distributive property. And if you carefully consider all of your factors and how they reduce, this is what you get. So now from here, what I'd like to do is I'd like to expand all of these pieces and do some heavy algebra. And now's a good time to distribute the A, distribute the B, distribute the C, and also the D. And now what I'd like to do is I'd like to shuffle pieces around so that like terms are with like terms, meaning group the powers of 3 with powers of 3, powers of 2, and then so on and so forth to get the following. And now what I'd like to do is I'd like to factor out the x's wherever applicable. And if you'd like, I can sort of put the x's behind the factor to make it look more familiar. And now realize that what we can do is we can introduce some zero terms on this side. This is what I'm saying. So I've done this so that I can compare the left with the right. Notice that the x cubed has to equal the x cubed so that the coefficients happen to equal one another. So I can create a system of equations is what it's called. So here's what I'm saying. Logically speaking, 0 would have to equal a plus c. 0, which is next to x squared, has to equal all of this, which is next to x squared. And then this 0 here would have to equal all of this there. And finally, 1 would have to equal a plus b minus c plus d. And so we have constructed here a system of equations, which must now be solved. Now, by looking at this, I would probably modify that upper equation. A plus C equals 0. Well, that means that A equals negative C. So by substitution, what I can do is I can go through the other equations. And instead of these A's, I can replace them with negative C. So let me write that second equation. So I have 0. I have 0 equals negative. That negative is here. Now, instead of A, I can write negative C plus B plus C plus D. Next equation, 0 equals negative, and then insert A, which is negative C, minus 2B minus C plus 2D. This bottom equation, 1 equals, and instead of A, drop in negative C plus B minus C plus D. Consider this here. Now, of course, these become positives. And then notice that in this middle equation, positive C and negative C knock out. So that just becomes 0 equals negative 2B plus 2D. I'll leave that equation alone for now. Now, what if we actually look at these equations here? What if you combine the second and the fourth equation and add them together? Let me add the second and the fourth equation. 0 plus 1 is, of course, 1. And then if I add these A's, they knock out, they're gone. If I add the B and the B, that would be 2B. These C's would eliminate. If I add the D and the D, that's positive 2D. So I've created here a tiny little system of equations, which conveniently can be solved because I'd have the B's would go away, so that 1 equals 4D. So D is 1/4. As soon as you have D, why don't you take it and plug it back in there to find B? So this is 1 equals 2B plus 2 times 1/4. So 1 equals 2B plus 1/2. So 1/2 equals 2B. So B is also 1/4. So we have B and D. We can go to this bottom equation because we know what B and D are. So let's see, I have 1 equals negative C plus, now we know what B is, it's 1/4. Take away C, we know what D is, it's also 1/4. So we have 1 equals negative 2C plus 1/2, subtract the half. 1/2 equals negative 2C. So that implies that C is negative 1/4. So we just need one more variable, A. Now recall what A is. A is just the opposite of C. So A would have to be positive 1/4. So we have A, B, C, and D. So now go back to pretty much where we started up here. And instead of A, B, C, and D, replace them with the values of A, B, C, and D. So let me just block this off here. So now our math looks like this. So this here, all of this is this, which is that, and this was this here. So the original math problem essentially becomes the following. It essentially becomes all of this. That is basically what this boils down to. So now the question is, how do I evaluate each of these individual integrals? So this first piece just becomes 1/4 natural log of x plus 1. This middle piece here, because it has a power of 2, you'd have to make a u substitution, where u is x plus 1 and where du equals dx. For more information, I can make another video on that if you want me to, but I'll just tell you what the result would be. That would be negative 1/4, and that would be x plus 1 to the power of negative 1. This piece would be minus 1/4 natural log x minus 1. And this one would be a minus 1/4 times x plus, or x minus 1 rather, to the power of negative 1. So let's clean this mess up, shall we? So we have and of course there should be a plus c. If you want, you could use properties of logarithms to actually combine these two terms into one. That would look like This can be further cleaned up for a final result of you can get common denominators if you so desire, but this is, I submit to you, a valid answer.